So we are trying to do the second question from electric fields structures worksheet. The A part is the same one, define electric field strength. So let's do the B part. A uniform electric field is produced by applying a potential difference of 1200 volts across two parallel metal plates in a vacuum as shown in figure 4.1. The separation of the plates is 14 millimeters. A particle P with charge 3.2 times 10 to the power minus 19 coulombs and mass 6.6 times 10 to the power minus 27 kilograms starts from rest at the lower plate and is moved vertically to the top plate by the electric field. Calculate the electric field strength between the plates. So first it is important to extract the information. So we have a parallel plate situation, and the top plate, the polarity of the plates are not mentioned. What we are given is the data that the voltage difference is 1200 volts. The separation of the plates is 14 millimeters, so 14 times 10 to the power minus 3 meters. Then the mass, the charge is given. The charge on that particle P is 3.2 times 10 to the power minus 19 coulombs. The mass is 6.6 times 10 to the power minus 27 kilogram. Calculate the electric field strength between the plates. So the same idea. So from E is equal to V over D is there, and E is equal to F over Q is there. We can't use this one because F is not given, though Q is given. But for this one, both V and D are given. So we are using that E is equal to V over D. 1200 divided by D, 14 times 10 to the power minus 3, gives you an electric field strength of 8.57 times 10 to the power 4 volts meter minus 1. Okay. Then the work done on P by the electric field. The work done on P by the electric field. A uniform electric field is produced by applying a potential difference. Okay, so what we have here is a positive charge. It is plus 3.2 times 10 to the power minus 19 coulombs. So what we have is a positive charge. And it is mentioned in the question that the plate, that the particle P starts from rest. Okay, it is mentioned here that the particle P starts from rest at the lower plate and is moved vertically to the top plate. So the particle is moving from the bottom to the top. So this is the direction in which the particle is moving, right? And it is moved from here to here. It is moved basically through the distance d, right? And the question is asking you to calculate the work done by the electric field. They are not asking you to calculate the total work done. They are only asking you to calculate the work done by the electric field, because there are two forces acting on the particle. Once it is in mid-air, one force is the force of gravity, mg, then obviously the electric force should be upward, otherwise the particle will not move upward. There are two forces, and both these forces are going to do work, but we are only concerned about, they are only asking you to first calculate the work done by the electric force. No issue, we will stick to the very basic definition of work. Work done is equal to force into displacement, the electric force into its distance moved. Now there is only one way to calculate the electric force, that is using this equation. So using this equation, F is equal to E times Q, so E times Q times D. But then if I look here, yes, I have found Q, the Q is found, the E is found in the earlier equation, so you can substitute E and Q. But the issue is E is something that you calculated in the earlier part, so if it was wrong, then here also you're going to get a wrong value. So rather than using E here, it's better to put V over D for E, so that even if there was a careless mistake, that would not influence this question. So instead of E, I am putting V over D, and then there is Q, and here is a D, so this D and D goes off, and you get W is equal to VQ. Now even if you start using this equation directly, the voltage difference times charge, it is acceptable, or else you can just quickly derive that equation. So you can start using W is equal to VQ directly, or you can come from the basic definition of work and derive this equation. Okay, so once we have W is equal to VQ, the voltage is 1200, the Q is 3.2 times 10 to the power minus 90. So this is the work done by the electric force or the electric field, which is equal to 3.84 times 10 to the power minus 16 joules. Okay, now it is good to remember this equation W is equal to VQ directly for the MCQs. As far as structure is concerned, it's better to get it derived, but as far as MCQs are concerned, it's better to remember this form. Okay, the work done when a charge moves through a potential difference V is given by VQ. Then you are asked to find the gain in gravitational potential energy. So the object is moving up. The particle is moving up from here to here, so its height increases by d. So the gain in potential energy, gain in gravitational potential energy is equal to mgd, right? So again, if you look here, this is basically the work done by the gravitational force, that is the work done by the weight mg times the distance moved. So gain in GPE, mg times d, m is 6.6 times 10 to the power minus 27, g is 9.81, and d is 14 millimeters, 14 times 10 to the minus 3. So that gives you that gain in gravitational potential energy as 9.06 times 10 to the power minus 28 joules. Okay. Then the question asks you to find the gain in kinetic energy of particle P. Now you can see it is like there is an object and that is being lifted by you. So the work done by you, let's say that you are lifting that object with a certain force, the work done by you becomes the kinetic energy and the gain in gravitational potential energy of the object, right? When you are pulling something, let's say that you are getting water from a well, or you are doing exercise and you are pulling a weight, the work you have done will be the kinetic energy gain in that for that object plus the potential energy gain. Similarly, here the electric force is doing a work, and that work done by the electric force becomes the gain in GPE, and the remaining will become the kinetic energy. Since initially the particle is zero, so the gain will be equal to the kinetic energy. So work done by the electric force will become the gain in gravitational potential energy plus kinetic energy, which means that kinetic energy is equal to work done by the electric force minus whatever the gain in gravitational potential energy. From the first part, we calculated that work done by the electric force as 3.84 times 10 to the minus 16. Now in the second part, we calculated the gain in gravitational potential energy as 9.06 times 10 to the minus 28. This gives you that gain in kinetic energy, or the simply kinetic energy, is 3.84 times 10 to the power minus 16 joules. If you look now, if you compare the potential energy and the kinetic energy, you can see this is 10 to the power minus 16, this is 10 to the power minus 28. This is almost 10 to the power 12 times the potential energy. The kinetic energy is about 10 to the power 12 times, because this is 10 to the power minus 16. The kinetic energy, potential energy is 20 minus 28. So that is about 10 to the power 12 times, right? So most of the work done becomes kinetic energy. In other terms, the work done by the gravitational force is very negligible. That means that the electric force is very, very, very large compared to the gravitational force. Okay. Then the last part of the question simply asks you to calculate the speed of P when it reaches the top plate. Now you know the kinetic energy. The kinetic energy is equal to half m v squared. So 3.84 is into 10 to the power minus 16 is equal to half times 6.6 times 10 to the minus 27 times v squared, which will give you a value for v 3.4 times 10 to the power 5 meters per second.